Mom, I have to do a research about the spiral. I don't know how to do, and I don't know what is it. Can you help me?
Oh, what a magnificent research you're going to do. Sometimes at school there's no time to talk about these subjects, but you will see that in it you will find maths history, suggestions, fascination, and you will learn to love maths more than now.
Oh, really, Mom?
Sure, my darling. Are you ready?
Yes, I'm ready.
Let's start. I would like to take your attention on what you see in everyday life. Both man and nature like the spiral shape. Humans like spiral for its distinctive trait and its undiscussed extreme beauty, so we choose it for objects we use in everyday life. For example, the riccio of a violin, a glass, the hairdryer's support, the shape of a screw, and so on. Can you guess now something in nature that looks like a spiral?
Mommy, I don't know. Wait a minute. Once I saw a seahorse and its tail was rolled like a spiral.
Yes, Julie, we can find spiral in nature too. Not only men prefer this shape, but some animals too. The chameleon has a tail rolled in a spiral shape, and so does the seahorse. Moreover, the horns on some animals, like rams, are rolled on themselves. And what about birds, Julie?
Birds? What have birds got to do with spiral?
Oh, Julie, even birds have something to do with spiral. For example, the peregrine falcon, the fastest predator bird we know, uses a spiral trajectory to reach and catch its prey. Because its eyes don't look straight to it, but sideways. It would be forced to look right and left, making its aerodynamics worse. So it follows this trajectory, looking its prey and keeping a high speed during its flight. There's no salvation for its prey.
Mommy, it seems to me that even some shells have a spiral shape. Isn't?
What a good observer you are, my dear. Yes, last summer we saw it in some shells on the beach, like the Nautilus, the Telescoptum, and the Gastropods family. And now, Julie, I would ask you a question. What about plants? When we go to Granny's house, didn't you notice something similar to this shape?
Let me think, Mommy. No, I don't remember. I can think anything like this.
Think about Granny's succulent plant collection. Did you notice something?
Oh, yes, it's true.
Yes, their leaves are in spiral shape, the cactuses, the aloes, and so on. It's the only way each leaf can have light and water in the same measure of the others. The disposition is called phyllotaxis, and it follows the shape of a spiral. We can say the same things for some vegetables, for example, the broccolo romanesco and the red cabbage in section, the disposition of the seeds in the sunflowers, and the pine cones. Even in the skies and in the space, we can find this shape. Hurricanes, cyclones, and depression areas seen from the space show us their wonderful spiral shape, and so does the galaxy.
It's wonderful, Mommy. I've always thought that maths was only on books, made of boring exercise and numbers. Now I'm starting to understand why you love it so much. It's because maths is everywhere around us. It's in nature.
Yes, Julie, it's just like this.
Mom, and what about arts?
Spiral have always fascinated men, so they used it in arts and in architecture as a decorative phrase. In ancient times, Greeks recognized the beauty of the spiral shape for the construction of capitals. Leonardo da Vinci used it to hold some of these paintings, such as Mona Lisa and Leda. Van Gogh and more recently Klimt used it in some of their paintings, Starry Night and the Tree of Life. It's used in architecture too for its beauty.
Mom, this is amazing. Now I'm very curious to know who studied the spirals in maths for the first time. Do you know?
Yes, Julie, you have to know that among the various spirals, we can have a particular one which is so mysterious and beautiful that is called magnificent spiral. A mathematician called Jacob Bernoulli studied it for the first time. He called it spira mirabilis because he found that it was very frequent to observe it in nature. He wanted to have it on its grave with the epitaph Eadem mutata resurgo, that means even though I am changed, I am still alive. The adjective mirabilis is referred to the fact that it has no hand. In fact, the central point, which is called pole, is reached only in an asymptotic way. Unfortunately for Bernoulli, the stonecutter sculpted a uniform spiral instead of a logarithmic one on his grave, but this is only a curiosity.
Okay, Mom, but I don't know that it's possible to draw a spiral simply turning around my pencil on paper. Please explain me how to draw a perfect spiral.
I will try to explain you in a simple way. A spiral is a curve with the following two properties. It has no symmetries. We can't obtain it over turning sideways or upside down. It's open, it has no end, and it's created by the rotation of a point around a second point called pole. It has two properties, homogeneity and self-similarity.
I don't understand, Mommy. Can you explain me the meaning of these words?
Homogeneity means that the structure is always the same. Self-similarity means that even if you make a spiral bigger or smaller, you will always obtain a spiral. This is the principle of the fractals.
Fractals. What are fractals?
A fractal is a geometric object with a property. If you look in it deeper and deeper, you will observe always the same structure. In nature, you can see a fractal structure in the broccolo romanesco, for example, because its minor parts have the same structure of the whole vegetable. Do you understand now? The first mathematician who studied fractal was Mandelbrot.
Mom, but how can I imagine the creation of a spiral?
Oh, yes, you can think about a semiline from the origin of axis. On this semiline, there is a point P moving with constant acceleration. The semiline is not fixed, but it rotates around the origin. The point on the semiline describes the logarithmic spiral during its movement. The constant acceleration of the point makes the shape of the spiral different from Bernoulli's one because it tends to enlarge its shape. There are some parameters that define the shape of the spirals, but an interesting case is when the segments are in golden ratio.
I'm starting to feel dizzy. What is golden ratio?
Let's think about a segment. We can divide it in many different ways, do you agree? But there is only one point C that divides the segment into parts AC and CB that are in golden ratio. This means that the ratio between AB and AC is equal to the ratio between AC and CB. If we say that AB is equal to 1, AC is x and CB is 1 minus x. This means that 1 on x is equal to x on 1 minus x. Now, if we solve this proportion, we find that it becomes an equation of second degree. For simplicity, I have supposed that the length of the segment is equal to 1, but nothing changes if you have another number. The second degree equation has only one solution we can accept, that is 1 plus square root of 5 divided by 2. This number is called golden number.
But now, why are we talking about the golden number?
Oh, Julie, it's strictly connected to the spiral. In fact, a scientist called Luca Pacioli discovered the link between the golden number and Fibonacci's sequence. Fibonacci was the son of a rich merchant in Pisa, but he liked mathematics very much. In 1201, Fibonacci wrote the book Liber Abaci, in which he tried to solve a problem about a rabbit's reproduction. He found a sequence of numbers which had a detail. Every term of the sequence can be thought as the sum of the previous ones. Luca Pacioli noticed that if we go on reading the terms of his sequence, the ratio between the sum of two consequent terms of the sequence and the previous ones approximate just to the golden number very well. It's not a case, it's everything strictly connected.
Mommy, but if I would accurately draw the logarithmic spiral, what would I have to do? Can you help me, please?
Yes, Julie, we need a golden rectangle. It's a rectangle in which, if we imagine to cancel a square with a side equal to the minor dimension, we always obtain a golden rectangle, that is, a rectangle in which the sides are in golden ratio. As we can see, the measures of the sequence of sides follows Fibonacci's sequence. If you draw some arcs of circles in every square, you will obtain a perfect logarithmic spiral. Will you try?
Yes, Mom, and thanks for this fantastic journey in the kingdom of maths.